thank you very much. I was asked to talk by Nora, who's not here, so thanks, Nora. I was asked to talk, but actually sincerely thank you, Nora, for inviting me. I was asked to talk on some work I did a long time ago on something called the Krohn-Rhodes theorem. And this is a paper I wrote very early in my career at the Santa Fe Institute. And I wrote it, and I was, took a long time to think things through. And I put it out there, and it had this sort of niche appeal among, obviously people with wonderful taste. It struck me today that this might be the time for people to start using this and to make sense of it. So I heard Paul got very excited about the Krohn-Rhodes theorem last night. So I'm going to teach you what the Krohn-Rhodes theorem is. We're going to have a little live demonstration of it. But let me begin by introducing or sort of bringing up sort of a big question that a lot of us have had over the years, which is what is computation? We're interested in how things think. We have some idea that thinking is a form of computing. So if we want to study this thing scientifically, we might start by brainstorming what computation itself might be. So one answer, a very simple answer, is that computation is an input-output relationship that has certain properties. So we have like some function here, m, that takes the input t and outputs p. So this turns out to be the mathematician algorithm. The mathematician function takes a statement of a mathematical theorem in some language, right? So some deductive logical statement or some piece of lean code. And it outputs proofs. So this is a mathematician, right? This is the mathematician computer. The red thing is the algorithm. The blue thing is the input, and the yellow thing is the output. So that's what a mathematician does. That's how a mathematician computes. If we think we understand what computation is, or we have some clear enough definition of it, we might ask ourselves, is there a science of this? So when I look at what we do when we build actual computers, we give them a series of instructions, right? Some kind of, maybe it looks like machine code, a series of sequential things we want the thing to do. But if we look at that machine code, maybe it actually has some kind of structure to it. Implicit in that code is some structure. So here's my Ruby code. I don't write Python, I write Ruby. I made the wrong bet on the future of interpreted languages, but and it's slowly dying. It's really sad. But if you compare this thing here, right, this long sequence of things that happen, like history, one damn thing after another, when you compare it to this, you start to see, wait, there's kind of like structures here. There's sort of nested structures. Inside this is this, and inside this is this, and maybe there's some like local things that can be glued together in some interesting way, maybe not piecemeal, maybe not like a quilt, but some kind of larger pattern into which these smaller objects can fit, right? So if you have that intuition, you might ask yourself, can we find like a kind of periodic table of these subunits? Is there a small number of subunits that we can compose together in some interesting or aesthetic way to produce arbitrary computations? I say aesthetic, what I might mean by that is that the mathematicians can find some structure to how they assemble. I might ask, are there uniqueness constraints to that decomposition? So I can, if I take my machine code, is there a sort of unique way to decompose it, or is there some way to identify equivalent decompositions? And because I'm an empiricist at heart, I also want to know, like, can I reverse engineer a computation? So if I see something happening in the world, if I watch mathematicians, or and I'll take some simpler examples. If I watch something, can I see what it's doing and decompose it into those subunits in the same way that a chemist might take some very complicated molecule and put it through a mass spectrometer and find the fundamental units? So these are kind of dreams we might have. Right? So how do we make that dream happen? One problem, of course, is that this is hard. It's hard to do this sort of thing. So just as a kind of thought experiment, you might think to yourself, well, if I decompose Simon's Ruby code into these subunits, but he's used these global variables, so in fact those subunits aren't really independent. They're actually using some scratchpad somewhere else in the system, so they're maybe not really as independent as we thought, right? all sorts of problems arise, at least when we go to the ultimate level of like Turing universal computation. So let's make this problem easier. This is the bargain. We're going to make this problem easier. We're going to do so by thinking about how there's a hierarchy of computational sophistication itself. So this is the Chomsky hierarchy, thanks to Noam. And it's like DEF CON. So DEF CON 0 here, right, is the Turing machine. And as you go to sort of weaker levels, you go to systems that can compute smaller numbers of things. There's things that systems above the Turing machine can't do, right? And this forms a kind of partial order here. So this is Chomsky. Here's the Jim version. Oops, sorry, let me put this up. Like, you know, unrestricted is all your machine code Turing machine stuff, right? Here are the context-free languages, right? These are languages that can recognize if you've nested your parentheses correctly, right? So there's your syntax highlighter is sitting here. Up here are we call the regular languages, and in fact, that's where we'll live. This is Jim Crutchfield's version from 1994. Jim, so kind of an old paper, but still a great one. Sorry?
Thank you for dating me.
This is a paper that came to Jim in a dream in the womb. And this is just to give you a sense that the Chomsky hierarchy is not the end of it all. As we've learned more about computation, we've been able to kind of parse out, you know, this guy here can do everything below it, right, but nothing above it. Up here are your universal Turing machines, and a lot of really interesting stuff happens here. These are the regular languages, and in fact, there's, as Jim has taught us, there's stuff below the regular languages yet, right? So we're gonna live right here, right on the boundary between the finite and the infinite, with these regular machines. So what do those machines look like? How do we represent them to ourselves, right? Here's an example. Here's a representation. Use that word informally. Here's a representation of a finite state machine. So this is a representation of a way of thinking, a pattern of thinking. It has two things. It has a finite number of internal states, which I've labeled A, B, and C, D, E, F, G, all the way to H. And then it takes inputs, and in fact, this is a really simple system. It only takes two kinds of inputs. So what happens here is that this machine is moving you around in this space. Let's say I start at internal state D, and I get hit. I get an input B, I go over here. I get an input A, I go down here. So I'm like, someone's talking to me, and I'm having thoughts, right? Hopefully, the way I work is a little bit more sophisticated than this, right? Or at least it has a more interesting representation than this. But this is where we're going to be talking. This is where we'll be living for the next 45 minutes or so. Finite state machines, these kinds of systems are actually reasonably common. They're quite powerful. If you've ever done a regex, this is a regular expression. It's a regular grammar. So here's a representation of here's how you translate the code of a regex that matches on a non-zero number of A's and then finishes with a B. That's how you represent this piece of computer code, right? This piece of regex code in a finite state machine. Here's another example of a finite state machine, the TCP/IP protocol. You have a computer sitting there and you're sending it packets, right? And as you're doing that, you're bouncing it through a set of internal states, right? So this here is a little calculator or a little algorithm that can find certain patterns in your data. Here's an algorithm that enables you to interact with another system. So these are finite state machines that we've created. Let me give you another example. I said I was an empiricist. So I got really interested for a while how people interact with each other online. So I got all the data from Wikipedia, in particular the edit histories of Wikipedia. So I can sort of scroll through and I can see what everybody's doing to the page. So you can think of the page as like a finite state machine, and people are denting it and kicking it around in different directions. So I was interested in modeling that process. What I can do here, I simplified the system a great deal. So I looked at these edits that people were making, and all I did was determine whether or not it was what was called a revert, where you've taken the page back to a previous state, or we called a C-edit, or a kind of creative edit that took the page to a new state. So here are examples. This edit here was a C edit. These ones here were all revert edits. So if I do that, I get a time series of C's and R's. And Wikipedia is great because I have a lot of C's and R's. Like I have a great, huge number of C's and R's. And out of the other side, I can reverse engineer a hidden Markov model of what's going on, right? So this is a model of the computation that collective group is doing. I'm tracking only a very small number of things, of course, in this page. I'm just tracking whether or not somebody did something, let's say, creative, although some of the creativity is a bit vandalism-like, or whether they did a revert. And so each of these states here is a state of the page. I've colored them. These are probabilistic models, so I've colored them yellow versus red, or sorry, yellow versus blue, group effect. C is if it's a creative edit, R is the revert. You can see that this system is like exploring some internal set of states, depending upon, in this case, there's only one input symbol, which is the passage of time. So I have, what I've done in particular here, I've coarse grained some of these things, and I get this kind of complicated internal model. Here's one more example of a finite state machine in the real world. So if you wake up and listen to bird song, right? You hear a bird in the morning, and the bird is like doo 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 doo, right? So there's some, they have these little stereotyped subunits that they string together, and people have fun. They can record them, coarse grain these sounds that the bird makes into sort of characteristic symbols, so a finite set of symbols. And then you can go listen to the bird, and you can model that process, that bird song, as a finite state machine. So these are just a few examples of where this kind of computation happens, either in engineered systems or in natural systems. Okay. So where have we gotten so far? Let me just summarize where we are. The first thing I said was I'm going to talk about computation. I'm going to talk about, in particular, not all Turing-complete computations, but somewhere on my Jim bestiary here of things. I'm going to sit right there. And then I taught you a little bit about what these systems look like. This is kind of an abstract representation. It maybe doesn't look like, you're like, well, that doesn't look like a piece of computer code that I've seen. And then I gave you some examples, code you might have written, right? So you yourself have probably written some finite state machine code in your life. We might have been, we might have built protocols to interact with each other that use these finite state things. And then some fun stuff that we can do sometimes where we actually try to induct from the real world the finite state machines that are sitting out there, right? So that's where we are, and then we have some questions, right? One way to think about this is that finite state machines, like they're not Turing complete, they're not way up here. One way to think, they're kind of online thinking, right? You're talking to me. As you're talking, I'm just transitioning from one state to another kind of instantaneously. It's sort of online processing that the system is doing. Any questions on this opening here? Yes, Scott.
Yeah, I'm wondering how you coarse grained in the finite state machine for Wikipedia, because I'm imagining that the number of states is going to be very large if it's the state of the Wikipedia.
Yeah, right.
And so I would expect that the graph that you get is completely a function of the way that you decide to coarse grain.
Exactly, yeah.
And maybe more generally with finite state machines, they'll have this property that since it's a not very expressive language, once you want to capture anything, you'll just get these massive, huge graphs.
Yeah.
And that is already a difference between what I think of myself and online thinking,
Yeah.
that it would be very inefficient representation.
Yes. Yeah, I think that's exactly right, Scott. So if each of these states here were trying to describe like the full, say it's a megabyte long page, so the 2 to the megabyte number of possible states that page could be in, that would be this machine would be sort of impossible to show on the page. So part of the trick of modeling real world systems is figuring out good coarse grainings to begin with, right? So if I imagine interacting with you, like let's say I'm a therapist, I'm interacting with you, I'm like saying things to you, your emotional state is changing, maybe I want to coarse grain that into a small number of states so that I can model you, which is not an unreasonable thing to do, right? Tom, I'll take your question in a second.
Okay.
So let's go on. So let's see if we can actually do what we sort of dream of doing, which is taking one of these machines, right, and decomposing it into subunits. So I'm going to do a little exercise here. Edmund earlier asked people to integrate a Gaussian distribution, a partial Gaussian distribution, and we sort of complained. So is Edmund here? Where is Edmund? Yes, okay, Edmund. So I'm going to give you a math problem. All right. So I'd like you to count mod 4, okay? And every time, I'm going to give you an input symbol. There's only one input symbol in this, so I'm just going to say beep. And every time I beep, I want you to start counting mod 4, okay? You can start wherever you like, okay?
0,
Beep,
1,
beep,
2,
beep.
wait, what?
Pretty tough, huh? All right. So, all right. Here are the 4 internal states that I asked you to do, right? And you got pretty close. You got a little confused. I get it, right? So here are the internal states of Edmund, right? And here's my beep sound, right? And so here's the algorithm I asked you. I sort of sketched out for you to do. Right?
I count at the beep. Got it.
Yeah, right. Well, it's a transducer, right? There's some subtleties there, right? So we won't do it again, right? I had a little machine there, and that machine was taking input from the outside and determining its the number of beeps mod 4. That's what I asked Evan to do. So here's a little finite state machine. Takes 1 input, 4 internal states, right? So if you look at this for a while, you're like, wait a second, right? I could merge these 2 states like this and merge these 2 states, and I get a simpler Edmund, right? I get a sort of subunit of the computation that Edmund is doing. So I'll write it like this. Right? So now, right, I have a simpler machine where I beep and it goes between 0, 2, and 1, 3. Right? So I've taken this finite state machine here, an incredibly complex, difficult calculation, right? And I've coarse-grained it, right? I've made a simpler machine, right? So this machine here, you may have noticed, this just tells you whether it's even or odd. So what I've done here is a partial, I've done a partial version of the Krohn-Rhodes theorem. So here's how, this is the Z4 machine, right? So this is the Z4, so Z the integers, right? This is the group mod 4. So what I've done is I've taken this large machine, and the sort of the top level thing is a Z2 machine. So it's this thing here. So I guess A is beep, right? Beep, 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 right? That's only part of the machine. I could just stop there, right? And someone would be like, what's Edmund doing? It's like, I don't know, but like, it's kind of similar to that guy who was doing, counting mod 6. Like there's this sort of super unit which is tracking even versus odd, right? And so, Edmund's counting even versus odd, Edmund's counting mod 4, Clem is counting mod 6, right? But I noticed, wait a second, both of them have this top level machine that's tracking even versus odd. So they're sitting up there. And then you're like, well, look, give me the full Edmund machine in your, very elegant procedural programming style. And so at the top level, it's this thing, and then he has a little sub-machine hidden inside. So this is a second machine here. The transitions of this second machine, let me just do this. The transitions of this second machine, right, the lower levels, respond to the same inputs from the outside, but in a way that's modulated or moderated or influenced by the higher level state. So if this is his top level machine, then he has a sort of nested machine inside, right, which has 2 states, C and D. And the transitions between C and D depend upon the state at the top level. So I go beep, right, say he starts in AC, right? That's his full state, AC. I go beep, A goes to B, and then I say, well, what happens to C? Well, I kind of look at this code here, and it's like, because I'm in state A, and I get the beep, I stay in state C. Then I'm at B now, so I beeped once, so now he's in state BC. I beep again, well, B goes back to A. I'm in state C, and I'm like, well, what happens here? Well, my little decomposition says, given that I'm in the higher order state B and I got a beep, I go to D. So this very laborious thing, I've just invented binary numbers, right? So 0, 0, 0, 1, 1, 0, 1, 1. And you can see how this representation here, this binary representation of counting, is implicit in this hierarchical decomposition that's happening here. Okay? So, like, lo and behold, we have a way to decompose complex machines into simpler interacting subunits. Any questions? Yes, question. Yes. Oh, sorry. Question and then question. Yes.
Sorry, is there a way to see that this is simpler, other than the fact that it's two parts that have smaller number of states? Because in some sense, the bottom one looks more complicated, putting them, than say something with four states, but just goes in a loop.
Right.
Like fewer options. Are you just thinking of the counting internal states?
So let's postpone that question. It's a really good question, right? A couple things that's nice about this, like one way that one thing I've done here is if I just blank out this, I have a coarse grain representation.
Yeah.
So Clem's counting mod 6, right? Edmund's counting mod 4, and I do the decomposition. I'm like, ooh, wait a second. If I just truncate the Taylor series expansion, right, out the other side, I'm like, well, they both have the first leading order behavior. That's one way to think of it, right? Another way to think about it is like they're not simpler, right? Sine x is really simple. The Taylor series expansion for sine x is like a mess, right? So simple is a kind of back and forth things. Question there, and then there, and then there.
Is it unique, the decomposition?
In this case, yes. Now, one thing is the order is ambiguous. So you can, in this case, like, oh, I moved that up there, I just changed the labels, right? But the order is ambiguous. Do you have other question or no?
In general, no?
In general, the atoms are unique, but the order is arbitrary in this case. Sorry, I forgot who was question. Yes.
Just so kind of understanding this, right? You couldn't do this like Z3 or Z13, right?
Ooh, you're catching on. It's almost as if those have no atoms inside of them, members of some kind of computational periodic table. Yeah,
Okay.
you're like, great, yeah, Clem.
Wait, so is this cascade product like a linear thing? Like you have three, so it can be boop, 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 or you can have a few which are like...
Oh yeah, so this is linear, right? So if I need another one down here, right? Spoiler alert in case the prime factors of my counting, there's more than 2 prime factors, right? I need more here, and of course what's going on here depends upon the states of the higher systems, the systems further up in the hierarchy. Yes, question?
Is there anything like stopping you from having a single state with a recursive arrow?
Good question. We'll get to that in a moment. All right. So that's the Z4 machine, right? You can see this is how the behavior of the nested lower level machine is depending upon stuff above, but not if there are any stuff below, not stuff below. So what I've just done is a very pretentious version of the fundamental theorem of arithmetic, which says that all integers can be factored into these atomic units, the prime numbers, right? Very mysterious, right? Elegant, beautiful things whose properties we don't truly understand, right? So that was my Edmund decomposition. In general, if I have a finite state machine where it is what we call reversible, meaning whatever state I'm in, I can figure out where I came from, so there's no merging, right? So if I have a thing that looks like this, like state Q, P, and Z, right? I get hit by A, in state Q I go to Z, and in state P I go to Z. I don't know where I've come from. This would be a non-reversible computation, but let's leave those out for a second. Let's say it's non-entropy producing, right?
Is this like co-unitular?
Sorry? I forget my translation dictionary, but good question. In this case, what I have actually is what we call a mathematical group, and so what we have is called the Jordan-Holder decomposition. So this is a 19th century result. Yes, question?
Is there a way to get Z mod 2 from the second level? Like the Jordan-Holder decomposition, the key thing is that there is an associated gradient on every level.
Is there what's
There is a group on every level.
Yes.
But is there a way to get a group from the second level, the more complicated sort of like
Is there, like, this is a group.
Z mod 2 from the second from the like machine with uppercase and lowercase letters. Where is the Z mod 2 hiding there?
So if I go back, right, in this case, like, I can say, okay, first just focus on how this machine behaves if I'm in the upper state A. Then actually it's the identity, nothing happens. If I'm in upper state B, now it's a cyclic, it's a Z2. So this is actually sort of, you can think of it one way, is this is actually two things, right? It's either the identity operation or it's the permutation or the Z2. Great.
Is that generic? Is it always the case that the group that's being represented by the lower level things is just like either identity or the explicit thing?
No, it could be other things as well.
Yeah.
So this could be, it's the six. There's not too many groups with two elements.
Yeah.
But yeah, so we'll get to more complicated things in a second. So here's your Jordan holder, right? In this case, you have more than just the integers, right? Your atomic units are the what are called the simple groups. So you have your counter groups, like your Edmond groups, right? You also have these alternating groups. You have the groups of Lie types, right? You have the Tietz group, Tietz pronunciation group. You have the sporadic groups. You have the monster group, right? So these are your kind of atoms now. This is your periodic table has gotten larger. If anyone starts a startup based on this, you have to buy this, the Atlas of Finite Groups. So these are all finally classified in the 90s, I think it was. So you can buy the world's most boring math book, which is just pages and pages of tables that are tabulating some of these remaining weirdos down here. Right? So that's the Jordan holder decomposition. So you might say, wait a second. Sometimes, like I'm modeling Scott in therapy. Not that Scott's in therapy, but I'm modeling Scott in therapy, and like there's something I say that always makes him mad. Doesn't matter what state he was in before, it always sends him to the angry state or the happy state, Scott. Right? In that case, right, that would be an entropy decreasing move, right? The thing has become irreversible. There's no longer an inverse operation that undoes. There's no undo key there, right? Because I don't know where I've come from. So if we include those irreversible processes, our machines go from being mapped onto groups, mathematical groups, to what are called semigroups. So for many, many years, we thought that semigroups didn't have enough structure to have one of these nice decomposition theorems. We had Jordan holder for a long time that said we could decompose reversible computations into these stacks of simple groups. But then these two guys, Edward Krohn and John Rhodes, together jointly proved the Krohn-Rhodes decomposition theorem, which said that all finite computational processes, so any of these things that you might draw, can in fact be decomposed in a hierarchical formulation. The atoms are the simple groups, so the ones you're familiar with from the Jordan holder, plus you have to augment it with this additional thing, which is the hard reset. Right? So in some of the levels, you'll see a certain computational move which sends all of the states to one state. So you just have to augment by one additional thing. Yes, question, Quinn?
Verbally you said semigroups, but then on the slide and just now you said groups.
Yeah, so if it's reversible, it's a group.
Yeah.
Right? But if there are moves in your system, like say there's a reset button, right? Now that finite state machine can no longer be represented as a group. It
says the simple groups.
Yep. So all finite computational processes can be factored into a series of atomic units. The simple groups come up very mysterious, and the forgetful free energy eating resets. So the decomposition.
Okay.
Yeah, so there are two things now. So you have to enlarge your periodic table to include not just the simple groups, but also these non-reversible processes that are like the simplest possible semigroups.
Oh, great. Okay.
Yeah. These resets are semigroups.
Resets are semigroups.
Yes, thank you.
Great.
Yeah, very good.
Thanks.
So the Krohn-Rhodes. So these are interesting characters. So John Rhodes, I don't know if he's still around. John Rhodes is like one of these cool like gurus, right? Like he's kind of like Stu Kaufman type, right? Krohn was his colleague, so they actually did this as their joint PhD. Edward Krohn did not live as good a life, and I think went to prison for kidnapping and murder later. Question, yeah.
Yeah, technical. Why did they say semigroup and not monoid?
Because you don't have to have an identity.
So
Technical answer to a technical question, yeah.
Okay, go on.
Because there may not be an identity, right? Like it may be that every input symbol always moves things away from where it was before.
But then you're not. Then you're saying that you have a collection of generators in a semigroup, right? Whatever.
Okay. Wow. Technical stuff. Yes. Clement and Scott.
So I was told earlier this week by Sophie that there's actually a hidden third thing that you have to decompose into, which is not the simple and it's like makes the whole thing really ugly,
No,
and it involves. Is this true?
no, I was just saying that the simple groups are cycles and simple non-abelian groups,
Okay.
which is how they presented in the theory.
Mm-hmm.
And then, so what's this weird hidden flag thing?
They're sort of like the monster ones in the.
Oh yeah, these weird exceptional groups and like these very strange simple groups. Like there's like the uranium of the
But
of them.
is
Yeah.
there like a mega uranium of the Krohn-Rhodes? Is that sufficient?
No,
Yeah.
no. The only thing you have to add are these really simple objects called resets. So I'll show you an example. There was a question in the back. Scott, yes.
Yeah, I guess I'm missing something that everybody else seemed to pick up on, but the connection between groups and these automata, I guess these are unary operations, the binary operations are in the group. So, like, what's the connection to groups?
So you have a you have a set of finite states, hidden states, right? I hit these hidden states with an input. It takes me to a new.
So the input is one of the elements.
Yeah, it's one of the generators of the group, and then we have the equivalence relationship as if any particular like two sequences of inputs are equivalent if for every hidden state that you start in, right? Doing those two things gets you to the same things on the other side. So that's the equivalence relationship.
Okay, so the elements of the group are equivalence classes of input sequences?
Yes, exactly. And the structure of the hidden states here is secretly encoding those equivalence relationships. That's another way to see how they're grouped.
Okay,
So
is
yeah.
there
the binary
a first
relationship
starting
is
state?
one sequence followed by one sequence.
Is there a starting state in the state machines such that we can,
No.
okay.
Yeah.
So then for all states.
Exactly. For all states, like input sequence X and input sequence Y are equivalent if they, for every input state, they produce like the same output state. So input state A, they all go to B, that's great. Input state B, they all go to C, that's good, right? So you have to match the transitions across all possible starting points.
Yeah, great.
So
Yep. Mhm.
maybe technical remark again.
Great.
I think my understanding is that you have the group or the semi-group, and the automata is like a representation of that group.
Yes, exactly.
But they're really two different things, strictly speaking.
They're isomorphic.
No.
Wow.
The representation is part of the
But anyway.
the representation and the collection of generators are both part of the data.
Yep.
And
So if I draw a finite state machine that's reversible, that's like that representation is isomorphic to a group, some group.
No. The representation it's a group representation pair. The category of reversible autonoma is the category of group representation pairs with some extra generators. Like the representation is a key part of the data.
Okay, so I don't know category theory, so I will trust you on that one. This is the pretentious book that will explain Krohn-Rhodes, except it won't. So at the beginning it talks about the pyramids. So here's a more sophisticated example. I showed you, this was my example of like a complicated finite state machine. And what I'm going to show you here is just the top level decomposition of this. So in the same way I took Edmund Z4 and showed you the top level was a Z2. In this case here's this big group, right? Or sorry, here's this big semi-group. Here's a big finite state machine, right? It's doing certain things, right? You give it, in this case it has two inputs, A and B, right? The top level representation looks like this here. So what is this, right? This is a cyclic group. So notice if you just look at A, it's just going womp, 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 womp. It's counting Z3, womp, 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 womp. So that's one element of this. The other one is one of these hard resets. Notice if whatever I'm in, I hit it with B, I go to BG, right? So you can see here, this wouldn't show up. If this were a group, you wouldn't get one of those resets because that's an irreversible operation, right? But what I get here is you can see Z3 is one of the simple groups, great, right? And the other potential thing that's happening here is a hard reset. So it all goes to a single state, right? So that's just good question. So let me tell you how this goes, right? So notice that state AH, that one there is mapping to those two. State BG is mapping to those two. State DE is mapping to those two. I might, however, be in CF, right? And in fact, CF are included in all three of these states. So if I want to know what's happening here, I have to look further down in the decomposition. So let me give you, here's another case. This is Krohn-Rhodes proved that these things existed, that you could do this, and that the decompositions took the form of either one of the simple groups or one of these hard resets. They didn't tell you how to find them in any efficient way, but people invented something called the holonomy decomposition, which enables you to efficiently find, I don't know actually what the computational complexity of it, but I think it's polynomial. So for an arbitrary finite state machine, I see your question in just a moment, an arbitrary finite state machine, I can feed it to this algorithm called the holonomy decomposition, and out the other side I get my stack. So here's another example of a stack. So here's a finite state machine that we began with, right? Top level, second level, and now third level. And you can see how at each level, right, the behavior of a lower level machine is contingent upon the states of the upper level, the machines further up the hierarchy. Question?
So I think I can kind of see how this will work with deterministic automata.
Right.
Maybe also non-deterministic ones.
Mm-hmm.
What about probabilistic ones?
So I'm going to punt on that one because I don't want to go through the whole construction, but there are, why don't I put a link in the Discord. So Jim sent me a very nice link to talk about how to do this. In the original paper I did in 2011, like I played a little game where you're basically selecting, you have a bunch of machines up here, right? You pick one of them at random and then you get the input signal and implement it. That's one way to think about a probabilistic transformations. I just pull apart the machines into deterministic machines and make it a choice over them.
So
And,
the
yeah.
theorem actually holds like this,
Krohn-Rhodes.
that holds for deterministic.
Yeah, so this is a story about how deterministic machines behave, and then it's up to you to figure out how to represent a probabilistic machine, for example, as a probabilistic choice over deterministic machines to get the decomposition. That's how I did it. There may be better ways. Yes, question?
I don't know which paper you refer to, but if you can, for example, when you have this Krohn-Rhodes cascade,
Yep.
you can constrain the information between the levels
Mhm.
so that the information that you send to the next level is constrained.
Mm-hmm.
If you do that, it's pretty ugly in the sense that you can actually get huge gaps in the grandeur when you make this trade-off of how much information you are allowed to transmit. And there are actually regions which are not stable. What in physics you would call them basically an energy gap or essentially an unstable equilibrium, and where there are no good solutions. And then when the information is sufficiently reduced, again you get solutions. So essentially it's not that neat if you do it this way with information constraints, for example.
That's interesting. I'll have to get the paper from you to learn more about that. In this case here, if I'm sort of inferring what you're saying correctly, in this case here, we sort of assume the information at a higher level, all of that information is available to the lower level machine, right? There's like a global variable sitting up here, and there's kind of a way in which that access is restricted, right? So you can think of these kind of nested codes. So what can we do with the Krohn-Rhodes theorem? This just has kind of been sitting here. I haven't seen a lot of papers on it. Occasionally somebody stumbles upon it. I sometimes get an email, or whoever else works in Krohn-Rhodes gets an email. And I haven't seen people do, like, I don't know what to do with it, right? So here are some thoughts, right? Like, let's create arbitrary machines, right? Let's actually wire these together, right? We can build these hierarchies. You notice that there's this linking rule that you have to figure out, like, so how the state of the top level machine influences the behavior at lower levels. But we can just start creating these, right? And just see what they look like. I have no idea, actually. I don't know where, for example, new abilities emerge in this hierarchy. One obvious thing to do is take finite state machines in the real world and decompose them and look at the top levels and second and third level and so forth. Groups. Look at, for example, one question is how deep they are, right? How long is that decomposition? Is that a good measure, for example, of complexity? And obviously, since Jim's in the room, like, let's understand how these hierarchies can be understood thermodynamically, right? So if I have a reset lower in the hierarchy, does that mean a more efficient machine, or is there no real notion of greater or lesser thermodynamic efficiency if the reset occurs lower down? One thing that's kind of fun is, let's say I take two interacting machines, like two people interacting with each other, so sending symbols back and forth. I can produce a joint machine out of that, which is the direct product of their internal states. When I do the decomposition, what does the top level machine look like, right? The coarse-grained description of two people interacting, what are those states? How do they mix the states of the individuals? Yes, Fernando?
Is there a way to quantify how much reset and how much non-reset there is at each level?
I mean, in one sense, yes, right? Like I have, generators at each, I have symbols at each stage, and I can just say, okay, is that a group or is that a reset? So when I just do the fractions, it's a great question, right? So like an obvious thing to say is like, let's use that number and then figure out like how thermodynamically efficient or not it is. Yes, question?
So, just a comment that I think this can also be related to Scott's comment that, one of the problems with finite state machines that for like realistic system we need a lot of states.
Yep.
But with the Krohn-Rhodes decomposition, you can have succinct descriptions of machines which have a lot of states.
Yes.
Because the size of the machine is
Absolutely.
exponential.
Absolutely, yeah. So I mean, I don't know, get a neural network to learn a finite state machine. Does it learn it in the Krohn-Rhodes order, for example?
You know the paper Shortcuts to Automata?
No.
It's kind of a big splash recently, and it's like, oh shit, Krohn-Rhodes is.
Oh, good. I've been out of the game for a while. Who wrote it?
It's very recent. I don't remember the author. Someone knows here.
Oh wow. Okay. Great. And I think maybe this is the final thing that I'm thinking about, right? Is like let's look at those coarse-grained machines, right? And see how they relate to the implementation in some real-world system like a neural network. So train a neural network to learn a big finite state machine. Okay. As the training goes on, does it learn the top-level decompositions first and then kind of figures out the lower-level ones? Can we see some parallelism between the structure of learning and this kind of mathematical decomposition that we get for free? Yes, Tom.
So a finite state machine is a generalization of the Boolean circuit, right?
A finite state machine is okay, let's say it is.
Is that true? I'm not sure.
No.
Okay, how would you
wait enough? Then everything is in one circuit.
Okay, so I guess one question I'm asking is like if you have like some feed-forward computation.
Yes.
And like one way of breaking that down is into like logic gates. I'm wondering if there's a way of reconstructing how the things that we see in Krohn-Rhodes into like the kind of logic gates that you see in a feed-forward computation. If there's like some kind of link there, or if these are like two very different ways of decomposing them.
So let's take a simple case where you have a Boolean function that goes Bn to Bn.
Yeah.
Right? In that case, I have my 2 to the n internal finite states.
Yeah.
I won't keep drawing them, right? And this might be 0, 0, 0, and this might be 0, 0, 1, right? And in this case, like this function here, this Bn to Bn map is just some kind of finite state machine that's interlocking all of these. It's moving you from one of these states to another. I stick this in, I get something else out.
Right.
If you by repeat it,
Your semigroup is the natural numbers.
Sorry?
Your semigroup is the natural numbers.
I don't know the natural numbers aren't a semigroup. Under addition they are, okay, so semigroup, but like this function here might just map everything to 0.
Yeah.
Right, so like, it's like the details of this function here will set up a particular machine here. So yeah, like take your favorite Bn to Bn function, right? And like, I don't know, let's look at the top level decomposition. It's an interesting question, right?
No, the composition here is boring, right? Like the natural numbers do not have an interesting.
It's, let me just table that because I don't know what you mean by saying that these, like every one of these Boolean functions here creates a finite state machine that's isomorphic to the natural numbers under addition.
The issue is there's only one input symbol. So
yeah.
You have the simple automata, they're not simple, but it's won't have very much to say about it because there's only one input symbol. It's like a kind of caching. But you could have
if you have one input symbol here, right? Let's just pause, right? Like let's say you have one input symbol, right? One thing could be that this is just some kind of permutation, right?
Yeah.
Another thing could be that it's got some resets, right? Some parts of the space are like hard resets, right? So there's some irreversibility in this, right? Like this might map any number large,
You know that your semigroup has a single generator. And
yes.
It's like the set of semigroups with a single generator is simple, right? It's either natural numbers or a cyclic group or.
It's like
Sure, yeah, but it's not very. It's like your atoms are going to be like the reset and yeah.
Yeah. So I don't know. Maybe that's like the carbon or something, right? It's pretty boring in the periodic table, but that's interesting, I guess. So yeah, one question is you got Bn to B. Another thing, of course, is that you just have like you have parity here, right? So how does this work? Another thing, of course, is if you have, and this is getting into this, you know, how many generators do you have, right? So let's say you have three functions, A, B, and C, right? So this is one of the Bn to Bn, this is another Bn to Bn, and so on. So what is this computation going to look like, right? One thing I guess I'm wondering is, yeah, what's the relationship between the circuit complexity of this thing, right, and some of the decomposition properties here? Yeah, question.
Yeah, going back to the framing of the talk at the very beginning, you had this little piece of Ruby code, and you were like, wouldn't it be nice if we could compose this somehow?
Yeah.
My first thought was that an equivalent formalization for computability is the general recursive functions, which just sort of already provide some kind of way to decompose it.
Well, so they provide a way to compose, but not necessarily decompose. So if you give me some machine code, right, there's no algorithm that will take that machine code and then output some kind of nice nested structure
it's
with these kind of...
to one, but there's no algorithm that will find it.
Right, and the other thing I wonder there, of course, is like, you know, if I take my Ruby code, right, and I'm like, oh, like, look, I got these nested functions, I just cut it here, I don't get a program, I don't get a valid program, right? I get something that's undischarged. Whereas the nice thing about these decompositions is I can just take that top level and just cut everything. I can take Edmund Z4 and I can be like, look, just cut to the chase, and it's Z2 at the top. So that's the other thing, is it gives you this nice way to coarse grain your system. As opposed to just re-describe it in a nice nested fashion, you can also kind of run that top level program as well. Like there's some sense in which that's doing something as opposed to just an undischarged nested function. Question, yeah.
So I think one thing that seems natural, you laid out like finite hierarchies of these like Krohn-Rhodes decompositions. Like what kind of computation can you do if you extend this to be allowed to be like sort of like an infinite descent of these? Like where does that sit on like the computation hierarchy?
That's a beautiful question, and I don't know the answer, right? The intuition is that there might be simple descriptions of countably infinite hierarchies that map onto cool languages in Jim's bestiary. And I don't know the answer to that, but that's a great question.
Well, it's not descent, it's ascent. If it was descent, it would just bottom out the prime numbers, and then you would run out of prime factors. But it's ascent. We're talking about building up more.
Yes.
Infinitely.
Yes. I was upside down. Other questions? Yes.
So yeah, automata, you can describe them by regular languages or regular expressions, or there are all these different ways.
Yeah.
Do you have any idea how that? Can I see the Krohn-Rhodes decomposition in these terms or something? I don't know.
Yeah. Right. Well, I mean, it's like they all kind of look like this, right? Sorry. They all kind of look like this. It's like you draw one, and then you run it through polynomial decomposition. So when I wrote this paper, there was GAP, there's like some algebra program. I'm sure there's got to be a Python package at this point. So you run, you take your finite state machine, you put it through the decomposition, you get something out the other side, and then the question is, so what, right? I mean, I think that's the real thing, right? So like, maybe what you do is you take a bunch of these, feed them in, and look at the top level ones and see empirically if some processes tend to have the similar top level behaviors, things like that, right? But in the end, like you can go drive yourself a little bit crazy by looking at these stacks and stacks and stacks of things. Yes, question.
Do I have something about the multiplicity of factors? Because like I have a bunch of 2-state factors, right?
They can be 3 though.
Well, they can be 3, but in this case, I have like multiplicity of 3.
Yeah.
Number of states 2 if you look at the set.
Yeah.
So can I derive like the multiplicities from like the number of like the alphabet and number of transitions or something?
Can you say that again?
Can I derive the multiplicity of how there's 3 factors that have 2 states each? Like, can I derive that from just counting the number of transitions or something?
I'm not sure if I understand the question, and I'm not sure of the answer.
Okay.
But we can take it offline. Yeah, my brain is just trying to track your question. I can't quite get it perfectly. But we know that that's not you. We could talk about that first. Yes, question.
What's clear is the composition is not unique. I'm actually trying to ask a friend, Christopher Nandin, who worked
Chris,
composition, whether there are any invariants about this decomposition that don't depend on.
So there are.
It's not unique.
Yeah.
Not unique.
But okay, primes is unique.
The order is not, unfortunately. So even the Jordan Holder has some degeneracies here. But I think that's a really good point.
I'm
Yeah.
trying to find out. I'm asking Christopher.
Well, that's wonderful. I mean, these are questions that I don't know if the answers in the literature.
I think that the actual atoms are unique.
The atoms are unique. It's the set of atoms with multiplicities.
But the
Yeah.
cascade product is not uniquely specified. So.
Right, the order in which this happens, right, and how these things link together. So I don't know, for example, if there is a unique way of linking these, linking the contextual influence, and I also don't know if the order of these. So for example, when we do things, we just list the atoms that occur, because we know that has to be unique, right? But I don't know, and I don't know, I mean, maybe Chris has some results on this.
Yeah.
One thing I think that's sort of sitting here, this reminds me a little bit, we're getting close to the end here, but it reminds me a little bit of SLT before people started applying it to actual data, right? There's all these results that are kind of sitting there. They're really beautiful. Maybe a slight perversion of these results in the same way you slightly pervert SLT to get, lambda when it's not in a local minima, right? That's, my sense is probably that's where some of the magic might be if people are interested. Yes, Clem?
It's just a cool thing. I saw a paper, I forgot the name, where they take systems of differential equations and then they apply some like generalization of Krohn-Rhodes to get like lead groups.
Yeah, so you can do this in the continuous space as well,
Yeah.
right? And a lot of what I've seen, like that's great, right? I remember reading those papers and being like, can I do anything with this? And I just couldn't see what to do with it.
Right.
And I think that's the challenge, right? Is figuring out how to translate these results. So yes.
So Alexander asked about the relation between these irregular expressions, and I think that if you look at the language of sequences that are periodic with some period n, then this has a simple Krohn-Rhodes. There's a simple Krohn-Rhodes description that captures it, but I think there's no short regular expression for this. So at least in some cases, it's more expressive than regular expressions. There might be examples which, in the other directions, could be probably comparable.
So you're saying that the Krohn-Rhodes will have a much more compact expression than regular expressions.
Mm-hmm.
Interesting.
Well, in fact, it's more troubling than that. So there is either you have your finite state machine's language, or you can write down the regular expression. In the case of having a finite state machine, there is a well-defined notion of minimal automata, minimal number of states. In the context, the grammar context, there is no notion of a minimal regular expression for language. So there's this ambiguity in measuring of complexity there, and there are a bunch of other similar differences. So you have to be kind of careful with this stuff.
Right. Yeah. One thing is, I remember reading about Krohn-Rhodes, proved I think in the late '60s, maybe early '60s. Mathematicians generally think this is as far as we're going to get. If you want any kind of like, if you want a decomposition like this for anything more or less structured than the semigroups, so semigroups have less structure than groups, the kind of general consensus is like no. Right, so this is like mathematicians like we're out at this point. Like many people didn't even think Krohn-Rhodes could be a thing, right? They proved it, like they were gutsy enough to prove it. But this may be the end of the line for these kind of periodic table fantasies. So I think that's something to bear in mind. After this, you're on your own. Yes.
Well, first of all, nobody uses a thing that is weaker. If you would use, that almost never occurs. But I've never used it. I don't know anybody who does. But there are actually lots of results extending Krohn-Rhodes in other domains. So you can use it, for instance, in tree languages. There's a similar Krohn-Rhodes, and
Right.
even languages that are like localized, so you can only do transition. Well, it's more like a category, which doesn't really matter. But anyway, there are all kinds of extensions in sort of different domains.
I mean, I guess what I'm imagining is that I would be surprised if there were languages that were not regular, right? That were sort of post Jim, right? They were in the infinitary place, or not infinitary, the infinite state case that had a Krohn-Rhodes without adding a lot of structure. Like certainly you can say, okay, look, here's a subset of regular languages. Here's the Krohn-Rhodes for them, and here's how I identify them.
No, but this is true. So the context-free languages can be embedded in tree languages, and they have a Krohn-Rhodes decomposition. So at least for context-free, it works.
That's really interesting.
What's
So
the
that's-
algebraic objects that the tree automata, the tree
Yeah,
regular?
they're tree automata, so they don't eat strings, but they eat a thing that is actually much more natural for computer science,
Yeah.
which is you're parsing expressions that are really implicitly trees. And then there's Krohn-Rhodes decomposition, and it's also context-free languages can be coding corresponds to.
I would love it if you put that paper in the Discord. That'd be great. And I'm out of time, so thank you very much.